Hello, my name is Robert Smith and I'm with New River Community College, and today we are looking at how to determine the nuclear binding energy of an atomic species. So we can get started. Basically what we're trying to do is find the, essentially this breaks down into finding the mass defect. So what we have is a difference between the atomic mass that is given here and the atomic mass if you were to sum up all the atomic masses of the various protons, neutrons, and electrons involved. Now, electrons are very small, so we're not going to worry about them as much. The order of magnitude is about 4 orders of magnitude less than that of the proton or the neutron. So we're just going to focus on protons and neutrons for this. It'll give us something that is extremely close to the correct answer, to the point where if you include significant figures, it is exactly the correct answer. So to do this, what we'll need to do is we'll have to determine the number of protons, the number of neutrons, and we'll have to find the total mass of protons and neutrons. So the number of protons is easy. You can read it right off there. So for protons, I'm just going to put a P for protons. We have to find the mass. That's equal to 83, because there's 83 protons, times the mass of a single proton, which would be 1.00785 AMU. And if you work through that summation, you get that the total mass from the protons is 83.649475 AMU. Now for neutrons, we have a mass that's equal to 290, or rather 209 minus 83, times the mass of the neutron, which is 1.008665 AMU. These are values that are available in your textbook. Now 209 minus 83 gives us 126. So 126 times 1.008665 gives us 127.091790 AMU. So the predicted mass, which we'll just call M, is equal to the sum of the mass from the protons and the mass of the neutrons. So we're looking at 83.649475 plus 127.091790, which will give us a total mass of 210.741265 AMU, which is different than the amount listed here. So we can take our delta M, our change in mass, our mass defect, and say that it's 208.9804 minus 210.741265, and that's going to give us negative 1.7609 AMU. That's our mass defect, and please be aware that we're using 4 digits after the decimal due to significant figure rules. So now we can use Einstein's classic equation, where delta E is equal to delta M C squared, which would be negative 1.7609 AMU times 3 times 10, it's 3.00 times 10 to the 8th meters per second squared. So this is going to give us negative 1.5848 times 10 to the 17th power AMU meters squared per second squared. Now, we don't generally deal with AMUs, so what we'll do is we will do a unit dimensional analysis. So we could say delta E is equal to this negative 1.5848 times 10 to the 17 AMU meters squared per second squared. And we can multiply it by the relation between 1 gram and atomic mass units. So for every 1 gram, or 1.00 grams, let's say that, you have 6.022 times 10 to the 23rd AMUs. That's Avogadro's number. And we can also convert from, for every 1 kilogram, we have 1,000 grams. So that'll put it into standard international units, which if you know your units, you know that kilogram, if AMU is getting replaced with kilogram, then we'll end up with kilogram meters squared per second squared, which is just the definition of 1 joule. So we end up with negative 2.6316 times 10 to the minus 10 joules. So that's our, that is what we initially looking for, the nuclear binding energy. It's taken as a negative because actually the binding energy will be positive. So we'll take the magnitude of that. It's done as a negative because we're looking at the change in energy, how the energy changed from from just having the mass of these particles versus this this mass defect causing that binding energy. So the binding energy is positive 2.6316 times 10 to the minus 10 joules. So very small. Now, to get the total number, the binding energy per nucleon, what we would do, so we're going to call this E bind. Per nucleon is going to be equal to 2.6316 times 10 to the minus 10 joules divided by the total number of nucleons. And we get that from our superscript right up here. So we're looking at 209 nucleons. So we end up with 1.2592 times 10 to the minus 12 joules per nucleon. So that's how you would go about finding the binding energy for a given species.